I'd like to introduce Rick Conklin onto the stage. Thank you very much.
Good afternoon, everyone. I am Rick Conklin from Dispersive Networks, here to talk to you about virtual networking and our programmable networks for mission-critical solutions. I've got about 112 slides in 10 minutes, so let's get moving. So what is it about a virtual network, or a programmable network that you should consider? Why should you consider those benefits over first-generation SD-WAN or legacy networking solutions? And the primary reason is that security and performance enhancements were never really built into these technologies. And they don't have the programmability, the API visibility that you need for advanced features. Our virtual network was designed with security from day one, with performance and reliability and high availability built into the platform, which is critical for meeting the use cases for mission-critical applications. Why? I think if you just take a quick scan of the news, it's all over the papers, at least in the States. Critical infrastructure, renewables, power industry, healthcare, hospitals, you name it, these are targets for attackers. Additionally, there's a paradigm shift in play. From a legacy perspective, we had very, very large sites, and we used a defense in depth kind of model to where there were layers to protect the assets in the network. And more, we're shifting into a zero-trust world where assets are maybe shifted into the cloud. You might have mobile devices, a large number of IoT devices, where the very first thing that we must do is authorize and authenticate the device. And a proper network in a modern world will first authenticate the device, authorize the device, and then only give that device access to the services and the servers that it's authorized to use. And it can do this very, very quickly. The programmability is through an API, so you can provide access to partners or users or even devices, IoT-style devices, on an as-needed basis, and then revoke that access as soon as it's no longer needed. And you can do that at an application layer, which means either an application ID or an IP address, port, and protocol need. Additionally, we're attempting to move the attack surface away from the edge, away from the asset node and into the cloud. There's a new push to do software-defined perimeter type of applications where the attack surface moves into the cloud. DOS and DDoS mitigation are best done in the cloud, and if you use SDP techniques with an authenticating control plane and an authenticating data plane with a call-out only model, you can literally make the endpoints disappear. We have use cases where a customer requires a very secure deployment, and with our software on it running legacy applications with no changes to any of the servers, the asset literally disappears from the network. If an adversary is doing an Nmap scan, they find absolutely no signature of that application or that server being present. But from the legacy application perspective, like I said, with absolutely no changes to those protocols, the services are still offered. And finally, the new paradigm, of course, is IoT. Large number of devices, very small footprints. It's no longer acceptable to require an MPLS line or other private line to all of these devices. It's not economical, and a lot of the legacy systems, especially in the SD-WAN space, require a large number of compute. Typically there's 4, 5, or 6 cores that are required to run these platforms, and these small IoT devices simply do not have the compute power in order to do this. From an availability and a performance standpoint, legacy SD-WANs, legacy communication protocols, are really single path point-to-point. If you think about the way that networks are built today, there's typically multiple sources of bandwidth. On the access side, you might have a primary source, perhaps a backup source, 5G, LTE, etc. And then, of course, the core of the network is a full mesh network with ludicrous speeds and ludicrous capacity. But the legacy protocols, the very first thing that they're going to do is they're going to find a single path through that network, and then the application or the user will remain on that single path for the duration of the session of the flow. And if there's a degraded scenario, the performance of the application or the user experience suffers, in the presence of an adversary, that session will stay on that link until there's some event. What a dispersive virtual network does is fundamentally different. Our network protocols are built from day one to be mesh aware and to be able to aggregate all the available bandwidth that's available to the device or to the user. If you're familiar with other technologies like equal cost multipath routing, they're essentially doing a hash on the flow which directs that flow to a single source of bandwidth and therefore to a single path through the network. And then it is simply balancing flows across bandwidth points that are available at the endpoint and through different routes to the network. We fundamentally operate different from that. We split the session up, or the flow up, break the packets into individual flows. We tunnel them either at layer 3 or layer 7 or layer 2, and then we encrypt all that information. So anyone, if an adversary is present, they will only detect that an endpoint is sending or receiving information into the cloud. There is no information leaked as far as DNS, as far as application ID, as far as user ID, and source destination information is also hidden from an adversary that might be trying to sniff the traffic. And that's important for use cases where an infiltration technique detects one endpoint, snoops the traffic, and then detects other endpoints in the network, and then attempts to compromise them from the information it's gathered. Additionally, because we are mesh network aware, we can steer traffic around outages, and those can be either planned or unplanned outages, and we can do that in real time. I'm an engineer by trade, and whenever I make claims, I like to provide evidence for those claims. We've been through a number of test ranges in the military space as well in the commercial space. This is just a short list of them, and we're very, very happy with the results. But like I said, I've only got 10 minutes, so I can't go into too much detail here. From a performance perspective, this is one slide detailing a few of the tests that one of our partners collected. This was a well-known SD-WAN platform that they used in addition to our product for more high-value services. And as you can see, the blue boxes, during lab environments, both platforms performed in a similar manner. But once we put these systems into a real-world environment, first across the continental United States and then internationally, you can see that our platform outperformed the competing platform significantly. And there's a number of reasons for that. We use a number of performance-enhancing techniques inside our platform. This particular test was for TCP, which TCP, it's a brilliantly written protocol, but it assumes that any lost acknowledgement is due to congestion in the core of the network, which modern mesh networks, ludicrous speeds, ludicrous capacity, and that's just a bad assumption to make. And we use a little bit more of intelligence, Bayesian probabilities, artificial intelligence, techniques of that nature to accelerate the traffic. And of course, since we're mesh network aware, we're able to take advantage of all the bandwidth and provide a better user experience. And we can do this for lossless flows as well as lossy flows, which are typically UDP-based, for real-time voice or other similar communications. Our target verticals, like I said, this is really intended for the high-value targets that require state-of-the-art security, as well as the high availability and performance that our platform provides. It's really a lot of military government customers, smart city applications, critical infrastructure and energy, which includes renewables, distributed energy resources, demand response devices, things of that nature, IoT, smart city, manufacturing, etc., and of course, financial services. Our carrier partners, we do work with a number of carriers in the United States, and mostly they're using this platform to target their high-value, mission-critical verticals. And it's really a differentiated service. Like I said, the programmability, everything is programmable through an API. All the monitoring points are available through database and API platform, which means that it can integrate easily with an OSS or a BSS system. If there's additional tools that you have for virtualization and visualization, as well as for analytics at machine time with either AI, neural network, or deep learning applications. We secure and optimize solutions right to the device, which is important in a lot of applications that we move that security to the endpoint, and a lot of our partners are becoming leaders in programmable networking really overnight simply by incorporating our software. Another aspect of our software is it's designed to be very easy to implement and maintain. We do a lot of things to provide CG-NAT type of capability, which greatly simplifies the deployment and adjoining IP address spaces and disparate networks over really any type of bandwidth. It really only has to be IP-based bandwidth. That's basically my time, so thank you very much. If you'd like to learn more about the dispersive virtualized network and the platforms where we're using it, the use cases where we're using it, please come talk to me or visit our website at Dispersive Networks. Thank you.
Thank you, Rick, and thank you to Dispersive Networks.